Hi students and friends, welcome to the channel Learn and Teach by Ayaz. This video lesson is about the topic HABER process. Syllabus learning outcomes are for the 2023 till 25 version for both CAIE 5070 and IGCSE 0620. So these are the learning outcomes. State the symbol equation for the production of ammonia in the HABER process. State the sources of the hydrogen, methane, and nitrogen air in the HABER process. State the typical conditions in the HABER process as 450 degrees centigrade, 20,000 kPa or 200 atm, and an iron catalyst. Explain in terms of rate of reaction and position of equilibrium why the typical conditions state are used in the HABER process, including safety considerations and economics. This is a simple equation for the production of ammonia gas from nitrogen and hydrogen gas. You see here that 1 mole of nitrogen gas reacts with 3 mole of hydrogen gas to give 2 moles of ammonia gas. This is nitrogen gas. This is hydrogen gas. This is ammonia gas. Forward reaction is exothermic, so we will write delta H minus. Hydrogen is obtained from methane. The process involves heating the methane gas with steam at high temperature and nickel as catalyst. It's an endothermic reaction and methane molecule breaks up to give carbon monoxide and molecular hydrogen. Here's the equation. CH4 gas plus H2O gas. CO gas plus 3H2 gas. Hydrogen can also be obtained through cracking of heavy fractions of crude oil or oil. Nitrogen is obtained by the fractional distillation of liquid air. In this process, air is liquefied first and then slowly warmed. Typical conditions in HABER process are 450 degrees centigrade, pressure of 200 atm or 20,000 kPa. kPa is kilopascal. Iron is the catalyst used here. You can even write Fe, which is a symbol for iron. The reaction is reversible and exothermic. And this reaction reaches to equilibrium state in a closed system. First, I will talk about the effect of reaction conditions on rate of reaction. High temperature increases the rate of reaction. This is because particles have more energy. Particles have more energy. They move faster and collide more frequently. They move faster and collide frequently. The collisions are more effective. Change in pressure also has effect on the rate of reaction because there are gases on both sides of the reaction. High pressure decreases the total volume occupied by the gas particles. Particles come closer to each other. Having more successful collisions. Therefore, the rate of reaction increases. Catalyst increases the rate of reaction by decreasing the activation energy of the reactant molecules. Effects on the position of equilibrium, concentration. Now we'll talk about the effect of changing concentration on the position of equilibrium. Increasing the concentration of nitrogen or hydrogen or even both will shift the equilibrium to product side. Increasing the concentration of reactant will shift the equilibrium to product side, or we can have high yield of ammonia. The reason is that to decrease the concentration of reactants or to increase the concentration of product. You can even refer the names of reactants and products here. Temperature. Forward reaction is exothermic. I will write here delta H is minus forward direction, which means backward reaction is endothermic. And we know that for a reversible reaction at equilibrium with exothermic forward reaction should favor low temperature. But here the temperature of 450 degrees centigrade is preferred. This is because if a temperature drops too low, the rate will decrease. Therefore, 450 degrees centigrade is a temperature compromise. 450 degrees centigrade is preferred because at low temperature, rate drops. But we can write low temperature will shift the equilibrium to right hand or product side. Theoretically, you can write low temperature shift the equilibrium to right hand side or product side. Reason will be either forward reaction is exothermic or backward reaction is endothermic. Forward is exothermic or backward is endothermic. Pressure. Now I will talk about the effect of pressure on the equilibrium. Here there are only gas molecules on both sides of the equation. 1 mole or nitrogen gas reacts with 3 moles of hydrogen gas to give 2 moles of ammonia gas. You can even refer to molecules or volume of gases instead of moles. Here, according to the reaction conditions, 200 atm pressure is preferred. 200 atm is preferred. This is high pressure. The pressure is increased, the equilibrium will shift to the side with less number of moles of molecule. High pressure will shift the equilibrium to the side with less number of moles, molecules, or volumes of gases. Here it is product side. The reason you can refer the number of moles, molecules, or volumes of gases. Either on reactant side or product side. So high pressure means there will be high yield of ammonia gas. In HABER process, iron is used as a catalyst. Is used as a catalyst. You know that catalyst increases the rate of reaction, but here catalyst has no effect on the position of equilibrium. Fe or catalyst has no effect on the position of equilibrium because catalyst just increases the rate of reaction in both directions. Here's a summary of this video lesson. Nitrogen can be obtained by the fractional distillation of air. Hydrogen can be obtained through cracking of heavy fractions of crude oil or oil. Typical conditions in the contact process, it's HABER process, 450 degrees centigrade, 20,000 kPa, 200 atm, and iron or Fe catalyst. The formation of ammonia gas from hydrogen and nitrogen gas is reversible, reaches to dynamic equilibrium state in a closed system. This reaction will counteract if there will be any change in either concentration, temperature, or pressure. The reaction is exothermic. It should favor low temperature, but temperature of 450 degrees centigrade is preferred. This is because if a temperature drops too low, kinetic energy of the particles will decrease and the rate will also decrease. Therefore, 450 degrees centigrade is a temperature compromise. Increasing the concentration of reactant will shift the equilibrium towards product side in order to decrease the concentration of reactant or increase the concentration of product. Increasing the temperature will shift the equilibrium towards the reactant side because forward reaction is exothermic or backward reaction is endothermic. Increasing the pressure will shift the equilibrium towards the product side because there are less number of moles or molecules or volumes of gases on product side or vice versa. There will be no effect of catalyst on the position of equilibrium because catalyst increases the rate of both forward and backward reactions. Thanks for watching. Press like, give comments, and share my video. For more videos, subscribe my channel and press the bell icon.